Hello students, welcome to EPG Pathshala. I am Professor P.N. Kodru from Jammu. Today we are going to discuss about a module entitled as Crystal Defects under paper Crystallography and Crystal Growth. So students, let us see what we are going to learn in this module. We are going to talk about crystal imperfections, different types of defects in crystals, classification of defects, concept of Schottky and Frankel defects, and evaluation of the equilibrium number of Schottky and Frankel defects. So let us first talk about defects in crystals. In an ideal crystal, the atoms composing it are supposed to be irregularly arranged. However, in real crystals, one finds some regions where the regular periodic arrangement of atoms breaks down. These regions are called defects, flaws, or they are also called as imperfections. The defects in crystals affect their properties. It is primarily because the crystals exhibit most of the properties which are structure sensitive. The presence of defects in them influence the structure sensitive properties, be it mechanical, optical, electronic, or any other. Defect in a solid is actually deviation from periodicity. The primary defects in crystals include phonons, electrons, and holes, excitons, vacant lattice sites, and interstitial atoms, foreign atoms in either interstitial or substitutional positions, and dislocations. These different types of defects can all interact with surface. However, they are usually found in the volume of the crystal and thereby contribute to the bulk properties of the solid. Defects in solids have been extensively studied, which makes it necessary to broaden their list by adding the following. Quasi-particles, such as the interacting electrons near the Fermi surface in a normal metal. Quasi-particles, namely Cooper pairs, in a superconductor where an attractive electron-electron interaction is induced by phonon. Quasi-particles, such as polarons, which consist of a conduction electron or a hole in an insulating ionic crystal, combined with a cloud of phonons. Polaritons, which are mixed states of photons and phonons, or of photons and excitons in insulating crystals. Plasmons, which are collective oscillations of interacting electrons in a solid. Magnons are quantized spin waves in a ferromagnetic substance. Fluxons are quantized flux loops in superconductors. Now we come to classification of defects. Depending on the type of defects, They are classified as point defects, line defects, plane defects, three-dimensional defects, electronic imperfections. Let us describe these defects in a slightly more detail. Let us first talk about point defects. If the defects are confined to a very small region of not more than a few lattice constants, they are called as point defects. Point defect is almost a zero-dimensional defect. The type of defects that fall under this category of defects include the following. Number 1, simple vacancy, or what is called as Schottky defect. Number 2, Frankel defect. Number 3, anti-Schottky defect. Number 4, substitutional impurity atom. Now let's talk about Schottky defect in detail. A Schottky defect is just a plain simple vacancy. There are no corresponding interstitial atoms or ions. It is a defect in which an atom or ion is found to be missing from its normal position in the lattice, as is shown in figure 15.1. Such defects occur in almost all crystals to some extent. If an atom or ion is not at its normal site but is found to occupy a position somewhere in the interstices, it is called a Frankel defect, as shown in the figure 15.2. It therefore involves creation of two imperfections, an interstitial atoms or ion and a vacancy. The third kind of defect, known as the anti-Schottky defect, is just a single interstitial atom or ion without there being any vacancy. When an atom is wedged into a hole which is generally too small for it, between the atoms which occupy their normal lattice positions, creates a defect known as interstitials. However, if an atom of the crystal is replaced by some foreign atom, the defect thus created is called impurity. A foreign or impurity atom is present in the lattice either at any interstitial position or at any substitutional position, that is, in place of any regular lattice site. The defect in the crystal falls under the category of substitutional impurity atom, as shown in figures 15.3 and 15.4. Here figure 15.1 shows a vacancy in ionic crystal, and figure 0.2 shows Frankel defect, followed by taking cation away from its lattice site and adjusting it into one of the nearby interstitial sites. Figure 15.3 shows an interstitial atom or ion, whereas figure 15.4 shows an impurity atom or ion. It may be noted that the presence of Schottky defects in a crystal reduces its density, while the presence of Frankel defects does not affect the density of crystals. The lattice will distort to some extent around the interstitial atom, and the amount of distortion will depend mainly upon the repulsive energy terms and the space available in the interstices of the crystal structure. In solids, such as closed packed metals, interstitials, atoms will have energy of formation. Energy to form Frankel defect is the sum of the energy to form the interstitial and the energy to form the vacancy. Such defects could be form of the interior of crystals due to thermal vibrations. It should be expected that some, though maybe a small number of the above set point defects to exist in thermal equilibrium, and the number shall increase as the temperature rises. However, which of these defects predominate will depend upon the relative energies of formation. A substitutional number of defects are formed in any of the following ways: by quenching from high temperature. Number 2, by radiation damage, for example, by irradiating with high-speed protons or neutrons. Number 3, by deformation or severe cold working. Number 4, interstitial foreign atoms are sometimes introduced by diffusion from the surface. Vacancies and interstitials have an important role in compound materials, particularly ionic crystals. In ionic crystals of a binary compound like NaCl, the various defects have a tendency to be created in pairs so as to preserve the stoichiometry by way of maintenance of equal proportion of sodium and chlorine. Secondly, the defects of one kind, as for example, creation of only vacancy of one type of ion, namely sodium plus ion or Cl negative ion in NaCl, would leave the crystal charged or would produce high electric fields between the interior and the surface of the crystal. So, in order to have charge neutrality, positive and negative ion vacancies must occur in pairs. Such an associated defect is neutral and so does not contribute to the electrical conductivity of the crystal. Type of defect involving pair of opposite charges is shown in figure 15.5. 15.5 shows Schottky defect, vacancy created by a pair of ions of opposite charge. Another type of defect occurs in ionic crystals when a multiple valent impurity ion, such as cadmium plus 2, is substituted for lattice ion. Divalent cations such as Sr plus 2, Ca plus 2 and cadmium plus 2 or etc. are reported to enter the lattice together with positive ion vacancies, thereby neutralizing the extra charge of the impurity. The vacancy may be either free in the crystal or associated with the cation to form a complex as shown in figure 15.6. Some of each type of these defects will generally be present in a real crystal. At any temperature above absolute zero, there will be some equilibrium number of these defects. Figure 15.6 here shows divalent impurity vacancy complex in an ionic crystal. At any given temperature, there will be a possibility of an equilibrium condition setup within a solid when the number of defects of any particular type which are created per second is the same as the number of defects of that type which disappear each second. The shape of the curve showing the number of defects present at different temperatures can be shown to be proportional to exponential of E by kT, where capital E is the energy required to create a defect of that type and K is Boltzmann's constant. The dependence of defects on temperature follows a curve of the shape shown in figure 15.7. Figure 15.7 shows dependence of number of defects on temperature. Equilibrium number of Schottky and Frankel defects. Let capital EV represent energy required to remove an atom from a lattice site to the surface. Then NEV is the increase in internal energy associated with the creation of N isolated vacancies. Application of statistical mechanics gives the total number of ways in which we can create these defects as W equal to n factorial upon capital N minus small n factorial expressed as equation 15.1, where capital N stands for total number of atoms in the crystal. From thermodynamics, we know that the Helmholtz free energy capital F is given by capital F equal to capital E minus capital T into capital S, expressed as equation 15.2, where capital S stands for the entropy and is connected to probability, and hence W through an equation S is equal to K log W. Substituting for S in equation 15.2 and using equation 15.1, we have capital F equal to small n into EV minus KT log of capital N factorial over capital N minus n small n factorial into n factorial expressed as equation 15.3. Using Stirling's approximation, log of capital N factorial is approximately equal to capital N log of capital N minus capital N for very large capital N, and making substitution in equation number 15.3 gives us capital F equal to small n into capital EV minus K into capital T within bracket capital N log of n minus small n log of n minus small n minus small n log of n. Del F by del N at constant temperature is equal to EF minus KT within brackets log of n minus log n. In equilibrium, at a given temperature T, the free energy is constant, and so del F by del N at constant temperature is equal to 0. Del F by del at constant temperature is equal to EV minus KT within brackets log of n minus log n fact is equal to 0. Therefore, EV is equal to KT log of n minus n by n, or EV by KT is equal to log n minus n by n, or exponential of EV by KT is equal to capital N minus small n by small n. For small n far less than as compared to capital N, exponential of EV by KT is given by capital N over small n, or small n is approximately equal to capital N exponential of minus EV upon KT, which is expressed as equation 15.4. This equation 15.4 gives the approximate number of Schottky defects present at any temperature T. One can similarly work out equilibrium number of Frankel defects in crystals. Equilibrium number of Frankel defects. Let EF represent energy required to remove an atom from a lattice site to an interstitial position. NF is the increase in internal energy associated with the production of small n isolated Frankel defects. Application of statistical mechanics provides the total number of ways in which one can create small n Frankel defects. W is equal to capital N factorial over capital N minus n factorial, small n factorial, cross n prime factorial over n prime minus small n factorial given as equation 15.5, where capital N stands for total number of atoms and capital N prime stands for the interstitial sites. Now the Helmholtz energy, capital F, is equal to capital E minus capital T into capital S, expressed as equation number 15.6. Using the relation between entropy S and the probability that S is equal to K log W, S will be given as K log within brackets capital N factorial over N minus N factorial cross N prime factorial over N prime minus N factorial, which is expressed as equation 15.7. Using Stirling's approximation, log capital N factorial equal to capital N log of capital N minus N and log N prime factorial equal to N prime log of N prime minus N prime for large number of capital N and capital N prime. Capital S, that's the entropy, is given by K N log N minus N log of N minus N minus twice N log N plus N prime log of N prime minus N prime log N prime minus N plus N log of N prime minus N. Substituting for S in equation 15.6, we have capital F is equal to N capital E F minus KT into N log N minus N log of N minus N minus 2N log of N plus N prime log N prime minus N prime log of N prime minus N plus N log N prime minus N. Del F by del N at constant temperature T is given by EF minus KT log N minus log N plus log N prime minus N. In equilibrium, del F by del N at constant temperature is equal to 0. Therefore, del F by del N at constant temperature T is equal to EF minus KT log N minus 2 log N plus log of N prime minus N equal to 0. Therefore, EF is equal to KT log of N minus N into N prime minus N upon N square, or EF by 2 KT is equal to log of N minus N raised to 1 by 2 N prime minus N raised to 1 by 2 upon N. Exponential of EF by 2 KT is equal to N minus N raised to 1 by 2 N prime minus N raised to 1 by 2 upon small n. For small n, far smaller than as compared to capital N prime, exponential of minus EF upon 2 KT is approximately given by small n upon capital N prime raised to 1 by 2, or small n is approximately given by capital N prime raised to 1 by 2 exponential of minus EF upon 2 KT, which is expressed as equation 15.8. As already explained, that in order to have charge neutrality in ionic crystals, positive and negative ion vacancies must occur in pairs. In the case of Schottky defect occurring in pairs, the expression at number 15.4 for equilibrium number of defects should get modified to n of the order of capital N exponential of minus EP upon 2 KT, which is expressed as equation 15.9, where NP stands for the number of vacancy pairs and capital EP is the energy of a vacancy pair, which is the energy required to remove a molecule, that is anion and cation, from within the crystal and carry to its surface. For a metal, EP is of the order of 1 electron volt, and at T equal to 1000 degree K, NP is approximately equal to capital N into exponential raised to minus 12, or NP by N is approximately equal to E raised to minus 12, which is equal to 10 raised to power minus 5. So, students, let us summarize what we have learned in this module. We have learned about defects in crystals. various types of defects in solids and their classification has been given. Point defects including Schottky defects, Frankel defects, anti-Schottky defects, and substitutional impurity atoms have been described and discussed. Dependence of number of defects in solids on temperature are also discussed. Expressions giving equilibrium number of Schottky and Frankel defects in crystals are derived. Thank you.